The James Webb Space Telescope, humanity's most advanced tool for exploring the cosmos, has begun delivering revelations that are completely reshaping how we understand our solar system. Pluto, once seen as little more than a distant, frozen relic at the edge of the Sun's domain, is now emerging as a surprisingly dynamic and mysterious world. After being reclassified as a dwarf planet and largely relegated to the margins, Pluto is now capturing center stage as scientists uncover evidence of geological activity, complex atmospheric phenomena, and even the potential for a vast hidden ocean beneath its icy crust. These discoveries don't just change the way we view Pluto, they challenge our assumptions about the conditions under which life might arise, opening the door to the possibility that habitable environments could exist in the most unexpected corners of the universe. At the heart of this transformation is Sputnik Planitia, the bright, heart-shaped expanse on Pluto's surface that has become its most iconic feature. Once thought to be an inert plain of frozen nitrogen, this massive basin is now believed to conceal a subsurface ocean that could extend hundreds of kilometers beneath the ice. Insulated by thick layers of frozen material and potentially warmed by residual heat from Pluto's formation or the slow radioactive decay of isotopes in its rocky core, this ocean could remain liquid despite the extreme cold. If confirmed, it would provide an environment where the chemistry of life might be possible. This revelation undermines the long-held idea that habitable worlds must exist only within the so-called Goldilocks zone of their stars. Instead, it suggests that warmth and energy can come not just from sunlight, but also from internal processes. Worlds far from the sun, orbiting in darkness, might still harbor life. Pluto's surface itself tells a story of extraordinary complexity. Towering ice mountains rise to heights rivaling the tallest peaks on Earth, made not of rock, but frozen water that is as strong as granite in Pluto's frigid climate. In contrast, the smooth plains of Sputnik Planitia show very few craters, suggesting the surface is constantly refreshed and reshaped. Scientists now believe that convection within the nitrogen ice acts like a slow-moving lava lamp, with material steadily rising and sinking, erasing ancient impact scars and sculpting new surface patterns. This process indicates that Pluto is geologically active, which is astonishing for a small, distant body so far from the Sun. Much like the icy moons Europa and Enceladus, Pluto appears to have a restless interior, hinting that the same forces that create life-friendly environments elsewhere might be at work here too. This activity is powered by the slow but steady heat generated by radioactive decay deep in Pluto's core. While modest compared to the immense energy driving the gas giants, it may still be enough to maintain liquid water beneath the ice for billions of years. On Earth, ecosystems thrive around hydrothermal vents deep in the ocean, entirely independent of sunlight, powered by chemical and thermal energy from within. The possibility that similar conditions exist beneath Pluto's surface, fueled by internal heat and protected by an insulating shell of ice, is one of the most tantalizing implications of the James Webb data. If true, Pluto could join the very short list of worlds in our solar system that may host environments suitable for life. Pluto's atmosphere adds yet another layer of intrigue. Composed mainly of nitrogen with traces of methane and carbon dioxide, it is astonishingly thin by earthly standards, but far more complex than scientists once believed. Its behavior is closely tied to Pluto's elongated orbit, which carries it on a 248-year journey around the Sun. When the dwarf planet swings closer to the Sun, even weak sunlight is enough to warm its surface ices, causing them to sublimate and thicken the atmosphere. As Pluto drifts farther away, these gases condense and fall back to the surface, creating a cycle unlike anything seen elsewhere in the solar system. This cycle allows researchers to study atmospheric dynamics under extreme conditions, offering insights that could even apply to exoplanets with unusual orbits. The James Webb Space Telescope has also revealed delicate layers of haze extending hundreds of kilometers above Pluto's surface. These hazes form from the interaction of ultraviolet sunlight with methane, producing tholins, complex organic compounds that settle across Pluto and its largest moon, Charon, painting them with reddish hues. The importance of tholins cannot be overstated. On Earth, similar prebiotic molecules are thought to have played a crucial role in the origins of life. While tholins themselves are not alive, They are chemical building blocks that, when combined with water and energy, can evolve into more complex organic structures. If tholins are interacting with Pluto's potential subsurface ocean, they could be catalyzing chemistry that leads toward biological systems. In this sense, Pluto may act as a natural laboratory, where the first steps toward life are quietly unfolding beneath a frozen crust at the edge of the sun's influence. Adding to the mystery is Pluto's unusual relationship with its largest moon, Charon. Nearly half the size of Pluto, Charon is so massive that the two bodies orbit a shared center of gravity located outside Pluto itself, making them more of a binary system than a traditional planet-moon pair. This close relationship has profound consequences. The tidal forces between Pluto and Charon generate heat in their interiors, providing another potential source of energy that could sustain geological activity. Charon's own surface reveals deep canyons, ridges, and polar patches of reddish coloration, hinting at a complex history linked to Pluto. Scientists now believe material, including organic compounds, may be transferring between the two worlds, creating a chemical exchange that could evolve over time. If this is true, Pluto and Charon may not only orbit together, but also share a dynamic, interconnected system where chemistry flows between them, increasing the chances for complex organic processes. None of this would have been possible without the James Webb Space Telescope. Equipped with powerful infrared instruments, Webb can peer through Pluto's icy shell, detect subtle temperature variations, and analyze molecular signatures with a sensitivity unmatched by earlier missions. While New Horizons provided breathtaking close-up images during its 2015 flyby, it could only scratch the surface. Webb's data go deeper, offering hints of Pluto's hidden ocean, the activity of its atmosphere, and the presence of organics that may hold the key to understanding prebiotic chemistry. In this sense, Webb has not only revived scientific interest in Pluto but elevated it to a priority target for future exploration. The implications extend far beyond Pluto itself. If such a small, distant world can sustain internal heat, geological activity, and possibly even liquid water, then many other bodies in the Kuiper Belt could also be dynamic and potentially habitable. Pluto may simply be the first to reveal its secrets. This possibility has already ignited discussions about future missions that could probe Pluto more deeply. Future exploration of Pluto could take humanity to unprecedented heights. Orbiters equipped with ground-penetrating radar could map the hidden ocean beneath its icy crust, while landers might drill into the surface to sample preserved organic compounds. Some even imagine robotic submarines exploring the subsurface ocean itself, a feat that would rank among humanity's greatest achievements, rivaling the moon landings and Mars exploration. While such missions remain technically daunting, they no longer seem impossible, especially as Webb's discoveries provide compelling reasons to pursue them. Meanwhile, Webb continues to uncover surprises. Observations suggest that Pluto interacts with the solar wind in unexpected ways, producing streams of ionized particles despite lacking a strong magnetic field like Earth's. This implies that even small, distant worlds can influence and participate in the broader dynamics of the solar system. Pluto is not an isolated relic. It is an active participant in the cosmic ballet, engaging with both solar and interstellar forces. For decades, Pluto was dismissed as little more than an icy leftover, too small and remote to command serious attention. But thanks to Webb, that perception has been completely overturned. Pluto has emerged as a frontier world, a beacon at the edge of the solar system that challenges our models and demands closer study. It represents not just a scientific curiosity, but a profound opportunity to explore the limits of habitability, to test how planets and moons evolve, and perhaps to glimpse the first sparks of life in a place where we least expected it. Its dramatic transformation in our understanding, from inert rock to dynamic world, from forgotten outpost to center of inquiry, marks one of the great scientific turnarounds of our age. In the years to come, Pluto may prove to be more than a frozen enigma. It could become a keystone in answering one of humanity's oldest and most profound questions. Are we alone? If the chemistry of life is indeed taking shape beneath its icy heart, then every new discovery brings us closer to understanding our place in the cosmos. The dwarf planet, once dismissed from the ranks of planets, now stands as a reminder that the universe holds its greatest secrets in the most unlikely places. Thanks to the James Webb Space Telescope, Pluto's story is only beginning, and with it comes the possibility that life itself may be far more common and widespread than we ever dared imagine. Pluto also forces us to reflect on the very definition of a planet. When it was reclassified in 2006, many saw it as a demotion, a footnote in the story of planetary science. Yet in light of Webb's discoveries, Pluto's scientific importance has only grown. Its small size and remote orbit have not diminished its complexity. Instead, they reveal that planets and dwarf planets alike can be diverse, surprising, and full of untold stories. Perhaps the lesson is that classification matters less than curiosity, and that even a world on the margins can hold the keys to cosmic questions as profound as the origins of life. Looking outward, the lessons of Pluto also extend to the study of exoplanets. If a frozen dwarf planet billions of kilometers from the Sun can sustain geological activity and potentially harbor an ocean, then exoplanets orbiting far from their stars, or even rogue planets drifting through interstellar space, might also be habitable in ways we are only beginning to imagine. The universe, Webb reminds us, is not bound by our preconceptions. Life may not require Earth-like conditions. It may flourish in hidden oceans, beneath icy shells, or through chemical processes powered by internal heat. For centuries, Pluto occupied a unique place in human imagination, largely because of its isolation and mystery. Discovered in 1930 by Clyde Tombaugh, it was celebrated as the 9th planet in the solar system, a symbol of discovery at the very edge of human knowledge. Early observations, limited by telescopes on Earth, suggested a small frozen world with little activity, a distant outpost quietly orbiting the Sun. For decades, Pluto was assumed to be static, a relic from the formation of the solar system with little to tell us beyond its size, orbit, and composition. This view was first challenged by the New Horizons flyby in 2015, which provided unprecedented close-up images. Now, the James Webb Space Telescope, with its advanced infrared capabilities, allows scientists to peer beneath Pluto's icy crust and study its atmosphere with extraordinary precision, revealing a world far more dynamic and complex than anyone could have imagined. Webb's observations go far beyond mere surface imaging. Its ability to detect minute variations in temperature and composition has revealed subtle geological processes, such as the movement of nitrogen ice across Sputnik Planitia, suggesting ongoing convection and resurfacing. These insights provide clues not only about Pluto's internal heat, but also about how small icy bodies can remain active over billions of years. Moreover, Webb has identified distinct chemical signatures within Pluto's atmosphere and on its surface, including complex organics like tholins. These molecules, formed through interactions between sunlight and methane, are thought to resemble the precursors of life, raising the possibility that chemical evolution may be occurring beneath Pluto's frozen exterior. Pluto's position in the Kuiper Belt is also significant. This vast, sparsely populated region beyond Neptune contains thousands of icy bodies, many of which may be similarly dynamic. If Pluto exhibits geological activity and potential subsurface oceans, it stands to reason that other Kuiper Belt objects might share these characteristics. The Kuiper Belt is not merely a repository of frozen debris. It is a laboratory of planetary evolution, where small bodies preserve the history of the early solar system while potentially harboring hidden environments for chemistry and life. Webb's data extend our understanding far beyond Pluto itself, providing a template for studying distant icy worlds both in our solar system and around other stars. Furthermore, the binary relationship between Pluto and Charon has profound implications for our understanding of planetary systems. The tidal forces generated by their shared orbit produce internal heating and geological activity on both bodies, creating a system in which energy and potentially chemical material are exchanged. Such interactions demonstrate that planetary habitability cannot be assessed solely by size, distance from the Sun, or surface temperature. Instead, dynamic processes, orbital interactions, and internal heat play critical roles in determining whether an environment can support the conditions necessary for life. The potential for a hidden ocean, ongoing geological activity, complex atmospheric chemistry, and the exchange of materials with Charon places Pluto in a new category of worlds, small, distant, and yet far from inert. Webb has transformed our perception of this once overlooked dwarf planet into that of a laboratory for understanding planetary processes and the origins of life. By studying Pluto, scientists are not only uncovering its secrets, but are also rewriting the rules for how we define habitable worlds and how we search for life in the cosmos. Pluto's story reminds us that the universe is far stranger and more complex than we often imagine. A tiny, remote dwarf planet has the power to challenge centuries of assumptions, revealing that life's ingredients and habitable environments might exist in the coldest, darkest reaches of the solar system.